Alright, so the final video for March 17, and so the thing that I want to talk about, of course, is how can we avoid thermal lensing. And it's a beautiful idea, actually. We exploit birefringence, and so the topic here is, beating thermal lensing beating losses due to, and actually instead of beating, this should say suppressing, because you don't entirely eliminate them, but suppressing losses due to thermal lensing by using a birefringent material. And it's a beautiful idea. Okay, so just to remind ourselves that what exactly is the problem that occurred, here's what we were saying earlier, that you have the gain medium and other elements cut at Brewster's angle, but Brewster's angle has been sort of decimated by the fact that because of thermal lensing, the refractive index of the medium, and so this element here, it's the gain medium that gets heated the most, and so this element is really the gain medium, and the refractive index of the gain medium is changing, so that means the Brewster's angle is changing. And so that means that now you actually are getting reflections. I mean, your polarization is not just P anymore. It's it's actually there are losses in both the S and the P polarizations. All right, and so that's a problem. So now you're getting. So let me just write here that. So I'm talking about the Brewster's condition here, that because the Brewster's condition is violated, there are now Brewster losses in reflection of both the S polarized and P polarized light. So what's happening is that previously, when there was no thermal lensing, then your light inside the cavity was purely P polarized, because you were satisfying the Brewster's condition for P polarized light. But now, because of thermal lensing, there's both S and P light inside. Okay, and the S polarized light, of course, has losses. So the more light that gets converted to S polarized siphons off power from the laser as a loss due to reflection, right? So let's see if I can write that down, that in other words, the more, and there's a name for this, these are called the more thermally induced depolarization loss occurs, the light that was previously pure P polarized at low power now sees itself increasingly converted to S polarized, because the Brewster's condition is not satisfied, which then has reflection loss. Okay, so it's not P polarized anymore. The light's becoming S polarized, and so there's a depolarization, right? The thermally induced depolarization that occurs. So actually, maybe I don't need this word in here. In other words, the more thermally induced depolarization occurs, the light that was previously pure P polarized at low power now sees itself increasingly converted to S polarized, and which then has reflection loss. So that's the problem. And how do we avoid this? And the answer is actually quite beautiful. What you do is make the gain medium extremely birefringent. Okay, so that's the idea. So let's see. So make light inside laser P polarized again. Now, so you're trying to make it P polarized. Now, just remember that there are losses in the P polarized also, because the Brewster's angle is not satisfied for P polarized light either. So yeah, you're depolarizing and light is getting converted to S polarized. S polarized light always has losses, reflection losses, but the P polarized light also has no losses only when this Brewster's condition is satisfied. As you move away from the Brewster's condition, you will have losses in the P polarized light also. And that's what I'm trying to say here, that you have losses in both the S and the P polarized. But I just want to show you that, remind you that still you want to make the light inside the laser P polarized. Because if you look at this graph, then the P polarized light, even as you move away from Brewster's condition, you still have low loss. The S polarized is always high loss. So you don't want to be in the S polarized mode. You want as much as your light as possible to be in the P polarized polarization, because even if you move away from Brewster's angle a little bit, the losses are not that great. Okay, so make light inside P polarized again, because P polarized light for small deviations from Brewster's condition still does not lose much in reflectivity, right? There's the reflectivity versus the angle. Much in P polarized light for small deviations from Brewster's condition still doesn't lose much in reflectivity, definitely much less than S polarized light. So we want to keep the light P polarized. So how do we do that? And the answer is that we're going to make the medium highly birefringent. Now, what does it mean? So make gain medium birefringent. Okay, so actually, sometimes you might hear of people using, materials people work with laser people very closely, and so this is what they're doing. I mean, so for example, a popular example, a popular high power laser material is neodymium doped yttrium vanadate. Okay, I think it's called neodymium doped yttrium vanadate. Okay, and this is a popular choice because it's highly birefringent, which is highly. So a lot of smart people, come together and try and figure out what the ideal materials are for lasing. So anyway, so that's why media like these are chosen. But anyway, how does this fix the problem? Well, if you recall what birefringence means that the material has a fast and slow axis. Okay, so this means that material has a fast axis and a slow axis. And what does that mean? That means that, remember, the S and the P polarizations are orthogonal to each other. Okay, so this means that the S polarization and the P polarization, so different speeds, right? That's what it means, different speeds for the S and the P polarizations. And that's kind of cool because that means that different refractive indices. Let's call that N sub S and N sub P for the S and P polarizations. Well, you might say, okay, so what? Well, that's very interesting because if the refractive indices are different, then that means that the mode spacing, the cavity mode spacings, remember how what the formula was for that? It was cavity mode spacing, so there was a delta nu, and this is equal to C over 2 times the refractive index times the length of the cavity, right? Well, this is interesting because now you'll have a cavity mode spacing for S and a cavity mode spacing for the P. Okay, and so these cavity mode spacings are different. Okay, cavity mode spacings for the 2 polarizations S and P are different. Okay, so now you can exploit the echelon trick that we learned in the last lecture, which implies can use an echelon or echelons to only pick or select one cavity mode, and it would be a p-polarized cavity mode, to select one p-polarized cavity mode. So remember, echelons allow you to make the laser single mode, and that single mode can be p-polarized. Okay, so how would you do that? Well, it's I have these graphs, this drawing to show you how to do that. So first, let me show you. So what am I trying to show you here? Let's see. So this would be, okay. So let's look at what I'm trying to show you here. Here you'll notice that I'm showing you a lot of modes, and there's actually two sets of modes. But let's just start. Start by saying that this thick curve here, this guy, is of course the gain profile. Remember that? Okay, that's the gain profile. Then what else am I showing here? Red modes. Okay, so these red modes, these red lines, you see them? The red lines, and there's red lines coming in. Okay, so there's a regular array of red lines here, right? So you see there's a red line there, there's a red line there. Okay, so these red lines. So the red modes, red cavity modes, are the thick echelon modes. Okay, so let's say we put in a thick echelon, and it has those red modes, right? So all the red lines, there's lots of red lines everywhere. And meanwhile, the green lines, you see that there are green lines here as well, green thin lines. Okay, so if you look in here, there's an array of green lines. And these green modes are the p-polarized modes, and the p-polarized cavity modes. Okay, so you'll notice that there are two cases right here, and right here, two cases where the green and the red lines lie right on top of each other. Okay, so these blue arrows are marking out the two modes where the echelon modes and the cavity modes are. So it's like right here and right here, and these are the cavity modes and the echelon modes are overlapping, coinciding, and so therefore the echelon will not permit any of the other green lines, cavity modes that are not lined up with itself, you see. So only these modes will laze. So what we have is two p-polarized modes allowed by thick echelon, right? But then, as discussed in the last lecture, you bring in a thin echelon. Okay, and the thin echelon, so these guys, the thin echelon has this, these are the permitted modes, right? So purple modes are the thin echelon. And the thin echelon, you notice, has a minimum for one of those modes, but a maximum for the other. And so now you have a single p-polarized mode. All right? So that's good. That's what you want. What about the S-polarized modes? You know, what happened there? And so that's the situation you want. You want the single p-polarized mode to operate, but in addition to the p-polarized modes, you also have the S-polarized modes rattling around. So in this case, I'm showing the red lines as above, okay, which are so it's still the thick echelon is still the red lines. They're right there, okay, just as they are above. Okay, and then so on, like there's a lot of red lines. The thick echelon modes are still there. The purple thin echelon modes are still there, just as above. Purple modes thin echelon. Okay, they're still there. The gain profile is shown, but you will notice that in this case, the lines, these lines, the cavity modes, these blue lines, okay, so there are blue modes, and these blue modes are the S-polarized modes. Okay, so the blue and the green and the red, all these modes are present in the cavity. Okay, but the thick echelon is, you will notice that the main point here is, what's the key point? The key point is that the green modes, P-polarized, and the blue modes, S-polarized, okay, these have slightly different spacing. Mode spacing, because of the birefringence. And what that means is that you'll notice that for the blue modes, this mode is not in alignment with the thick echelon. So the thick echelon is able to eliminate one of the where there would have been a S-polarized mode lasing. It gets eliminated, and so there's only one place, only this guy, okay, is able to lase in the cavity. So that's why thick echelon can permit two P-polarized modes, but only one S-polarized mode. You see, it is able to eliminate one of the S modes, and just one is left, and that one is eliminated by the thin echelon. So can permit two P-polarized modes, but only one S-polarized mode. And this S-polarized mode is eliminated by the thin echelon. So the twin echelon combination, you see, is able to eliminate the S polarization, the S polarized modes, and you're left with just a single P polarized mode, and the single P polarized mode does not have much loss when you deviate from the Brewster's condition. Okay, and so this is a very nice way to get rid of thermal lensing, because otherwise thermal lensing is a big problem that high power lasers face. If you have any questions and all, I'm going to after spring break, I'm going to try and do live streaming lectures, because clearly, I can imagine people having questions, and I'm just sort of motoring along here by myself. Okay, so hopefully this made sense about the thermal lensing, why it's a problem, and how to fix it. Okay? All right, I will be in touch with you again soon, later. Thank you guys. Thank you everyone.